We are now going to continue the chapter 7 notes. This is part 2. So this is all about light. And so we talked about how light is part of the electromagnetic spectrum. There's many different types of light. There's infrared, there's ultraviolet, X-rays, gamma rays, radio, microwaves. These are all types of light. Only just some of it is visible. Most of it is stuff we cannot see. So what in the world is light? And so one of the things about light was considered what's called the black body problem, solved by this guy named Max Planck in 1900. What is this black body problem? That is partially kind of like, well, why is light always given off in these same kind of units? Light is always given off in the same discrete units, also just called quantum. Quanta is plural for quantum. So you might have heard of the term quanta. It's always emitted or absorbed in these units. When I burn a piece of log of a piece of wood, is usually kind of like a reddish, orange, yellowish kind of light. Whereas if I heat up gas from a stove, that light is usually blue. And it's always, even if I turn it up hotter, higher flame, it's just bigger blue flame, or smaller flame, just smaller blue flame, but it's always the same bluish flame. It's not really changing colors. It's the same frequencies, same wavelengths. They're always the same units of energy. And these units of energy called quanta or quantum singular, quanta plural, is part of this black body problem. He said that light that is given off, hold on, am I pushing the right button? Oops, sorry, too far. Okay, so light is given off in these units of energy, and these energy, or these packets of light, E for energy, is equal to a constant h times nu, nu being the frequency. Energy of light is equal to a constant times frequency. That constant is called Planck's constant. The symbol is h. It's just a symbol. H is Planck's constant. H being 6.63 times 10 to the minus 34 joule seconds. That is Planck's constant. So, in other words, since this is just a constant, the higher the frequency, the higher the energy. The lower the frequency, the lower the energy, because H doesn't change. It's kind of like, another constant would be pi, kind of like 2 pi r for, your circumference. The bigger r is, the bigger the circumference is. Well, in this case, E is equal to h times nu. The bigger nu is, the bigger E is, energy. And I actually want to go back to that last table with frequency, okay? High frequency on the left side, low frequency on the right side of our electromagnetic waves. So visible light, just somewhat in the middle, but low energy, radio waves are low energy waves. Infrared, lower than visible. Higher than visible light will be ultraviolet light. And I kind of mentioned before, that's why, since it's higher energy, they also can damage, say, your skin, which is why you apply sunscreen if you go out to the beach or if you have exposure to sun. This ultraviolet light can damage your cells long term. Even higher than that would be even higher than ultraviolet light would be X-rays. When you go to the dentist's office and they take X-rays of your teeth, they usually cover your body with this heavy vest. Usually there might be lead or just some heavy, massive material in it. It absorbs X-rays so that it doesn't really go too much into your internal organs, into your body. Yes, it does go through. We need to have image of your teeth. That's why you're at the dentist's office for that. But the X-rays in general are actually high energy, and they can be dangerous. Which is also why the dentist or the hygienist, whoever's doing your X-ray, when they're taking your X-rays, they leave the room. They go behind a thick wall because you have x-rays. I don't even remember last time I had an x-ray at a dentist, maybe a couple of years ago. So you have x-rays every, not too often. The dentist or the hygienist, whoever's doing x-rays, is doing this multiple times a day. So they have to go behind a wall because high energy or high frequency, high energy. So going back to that slide, high frequency, high nu, high E, high energy. Okay, H is just a constant, doesn't change. 6.63 times 10 to the minus 34. Okay, next thing, something called the photoelectric effect, which was solved by this guy named Einstein, which I know you've heard that name before, in 1905. Einstein actually won a Nobel Prize in physics for the photoelectric effect. Not as, even though he's more probably known, you probably have heard like theory of relativity, that kind of stuff. Yes, he's obviously famous for that, but he already won the Nobel Prizes initially in 1905 for the photoelectric effect. What is the photoelectric effect? Basically, here is a metal, outer metal, inner metal, and there is a glass container, so no particles can go in and out. Only thing that can go through it is light. When exposed to high energy light, what he noticed was there was a charge difference that he could read in a voltmeter between the outer metal and the inner metal. And that was only, why would there be a charge difference? That's because light did something to the outer metal to knock off these electrons. And electrons flowing is electricity, why there was a difference in electric voltage. So from that, he hypothesized or told us that light is not just energy, it's not just a wave, but it's also a particle. That particle of light called a photon. Okay, light acts as both a wave and a particle. So it acts like a wave and a particle, but this particle, it's in quotes, this particle of light has no mass. Unlike, waves of water in the ocean, or even waves of sound. Sound is, my vocal cords, lungs, whatever, pushing the air. If there was no air, you wouldn't hear anything. If there was, sound actually has to go through something. So it has to go through the air, it can go through water, it can go through, but it must go through mass, something with mass. Light, or a particle light, a photon, does not require a medium, does not require anything for it to go through. It can just go through space. In space, there are no particles, but light can go through it. It's kind of like a particle, but it also acts like a wave. It's both. So Einstein basically said that light is both a particle and a wave. Okay, we don't need to know this bottom part down here. Okay, so let's do one of our first problems. When copper is bombarded with high energy electrons, X-rays are emitted or given off. Calculate the energy in joules associated with photons if the wavelength of the X-rays is 0.154 nanometers. Okay, so our equation is this. E is equal to H times nu. So energy is equal to Planck's constant H times nu, the frequency. We're actually not given the frequency. All we're given is the wavelength. The wavelength is 0.154 nanometers. But that's okay. If I know the wavelength, I can solve for the frequency. How do I do that? Let me go back to that back to the slide here when we did this before. Wavelength times frequency is equal to speed of light. So in other words, frequency, nu, is equal to speed of light c divided by lambda. So lambda times nu is equal to c, nu is equal to c divided by lambda, or lambda is equal to c over nu. But go back to that thing. Nu is equal to c divided by lambda. So energy of the light is equal to h times c. H is Planck's constant. Planck's constant, you would be given, it's right here, 6.63 times 10 to the minus 34. So h is a constant, c is a constant, the speed of light, 3.00 times 10 to the 8th meters per second, and the wavelength. Though our wavelength is in nanometers, it actually should be in meters. There's 1 billion nanometers in a meter, so divide by 1 billion. So this is H, this is C, and this is the wavelength in nanometers. in meters. The reason why I have to change nanometers here to meters, and I do that by dividing by a billion, there's a billion nanometers in a meter, is so the units meters and meters will cancel out. So seconds and seconds cancel, and the meters and meters will cancel out. So the energy will be equal to whatever 6.63 times 10 to the minus 34 times 3 times 10 to the 8th, all divided by 0.154 times 10 to the minus 9. This is all in the denominator. And what is that in a calculator? Type in a calculator, you get 1.29 times 10 to the minus 15 joules. So if you had copper and bombard it with X-rays, and the wavelength of that particle of light, which you would not be able to see because it's an X-ray. Humans cannot see X-rays. The energy of that particle of light would be 1.29 times 10 to the minus 15 joules. Okay, so that's the amount of energy of a particle of light. Okay, going on. I want to get to another thing called emission spectra. I'm going to put myself up here for now. Okay, so if I had a light source and I sent that light source, through a tiny beam of light source through a prism, we can break it down. And actually, this light source, maybe I should actually be clear, if you take any material, let's just assume it's in a gas form right now. If you have a gaseous material, whether it's carbon dioxide, neon gas, helium, hydrogen, pick a gas, okay? But let's just stick with the gases right now. And you send high voltage electricity through it, it'll start glowing. In fact, that's what neon lights are, okay? It's a tube of gas, and you send electricity through it, and inside that gas, it starts glowing. Yes, neon lights are different colors, okay? But you take that light and you shine it through a prism, it will break apart into what's called its line emission spectrum. This is the line emission spectrum of hydrogen. If this was hydrogen gas in here, and you sent electricity through it, hydrogen's just a gas, it will start glowing, and that that light, if you shine it through a prism, it will be broken down into 4 distinct lines, as shown in this picture. Well, we did that with not just hydrogen, but we did it with a whole bunch of different elements. And not just elements, you also do a carbon dioxide, you do it with a whole bunch of different compounds. And on the next slide, okay, maybe I'll move my face over here-ish. Whatever, this top corner for now. Okay, so this is the emission spectrum, spectra plural, spectrum singular, of a whole bunch of different elements. Here's hydrogen. It might be hard to, I can see on my screen. You could see that I see this 1, 2, 3, 4 lines with hydrogen. If I had helium, if I put helium in this tube and I sent electricity through it, and I took that light and shined it through the prism, helium would have these distinct bands of light. Neon gas. If you took neon gas and put it in a tube, sent electricity through it, shined it through a prism, you would see these distinct lines. Argon and so forth. And they don't have to be just gases, they can be metals, but we have to put it in a gaseous form. Okay, these are types of light. Notice what we can see about it. And his important point is no 2 elements are the same. No 2 compounds have the same emission spectrum. That's kind of like our fingerprints. Yes, if I had my fingerprints taken, if I put it, put my fingers on ink and then, I put it on paper, and we all did that. As you know, no 2 people have the same fingerprints. And even though aren't they just lines? Well, these are just lines. Why can't 2 elements have the same? There are no 2 elements. There are no 2 compounds that have the exact same emission spectrum. And so why is this important? This is actually one of the bases of astrophysics. Okay? If I took light from a faraway star, okay, it's not totally made up. If you take light from a faraway star and you took that light from that star and sent it through a prism and you saw its emission spectrum, like here is the light from this unknown faraway star, then you match it up with all the elements that we know here. What do we get? Well, what can I say about the star? I can say, hey, you know what? I've never been to that star, but I know what that star is made up of. Because of the light that comes from that star, and its emission spectrum. And its emission spectrum matches that of, say, I don't know what, hydrogen. So these bands of light matches with hydrogen. That star is made up of hydrogen. Just like if I have a suspect with their fingerprints, I can match it up with, well, here are my known people with their fingerprints. Well, they're not fingerprints, they're emission spectrum. Then I can match up the suspect with the known fingerprints. That's exactly how we determine what the elements are on another star, another planet, is the light that comes from it. We didn't go there. We never went to another star, okay? Our closest star, the sun, I mean, when you don't really go to it, it's too hot. But how do we know what elements are from these, other planet? It's all from the light that comes from it. Whether it's visible or invisible. I mean, okay, this is visible light. Okay, this is visible lights for humans to see, but now we know, of course, there also could be X-rays, there could be infrared light, ultraviolet light, gamma rays, all different types of light but this is just with human eyes. If we were actually at Pali in class, I would actually have you take a type of prism inside this little type of viewing device, and you would be able to see the emission spectrum of all different types of elements and try to match that of, other ones. Kind of like, actually would have this on the screen and say, what element is that's inside this tube that you don't know? Well, you just look at the light and try to match it up with one of these up here. Okay, anyway, so that's emission spectrum. That's kind of the general basis of astrophysics. Okay, one last slide for today. Bohr's model of the atom. This is the model of the atom that you learned in middle school. Center would be the nucleus, surrounded by shells of electrons. Okay, photon is given off. We'll get to why. Okay, but oops. Bohr's model of the atom, 1913. He said that hey, you have the nucleus center, and you have different levels of electrons. And why do we have these different levels or shells of electrons? Because electrons, E minus, that stands for electron. Electrons can only have specific or quantized values, energy values. And so because of that...
Here are some results.
Okay, thanks, Alexa. I don't need your reply. They're only different levels of energy. And so that's why they have certain shells. Why is light given off? Light is given off as electrons go from one energy level to a lower energy level, from a higher energy level down to a lower energy level. So, well, first of all, how to get to higher energy level? When you take a substance, you heat it off, somehow you give it energy, okay? Whether you heat it up or whatever. As it absorbs energy, the electrons goes from one level to a higher level. Well, eventually, like gravity, but it's not gravity, it falls back down to what's called its ground state, its normal state. And as it falls back down, that energy has to go somewhere. And as light is given off, as electron goes from one energy level, a higher energy level, down to a lower energy level. So conservation energy, as electron goes up because it gains energy. As it falls back down, it gives off energy in a particle of light or a photon. So that's how light is produced. Again, I'm talking about not just visible light, but also X-rays, gamma rays, etc., etc. Okay, the amount of energy of any level is equal to minus RH times 1 over that level squared, where n is the shell or principal quantum number, first shell, second shell, third shell. And we'll get to that term a little later, but principal quantum number is the technical term. You might have just called them shells. Okay, first shell, electron, second shell, third shell. They're technically called principal quantum number 1, 2, 3, and it goes on 4, 5, 6, 7. And RH is called the Rydberg constant, 2.18 times 10 to minus 18 joules. We're not going to do problems with this right now, but we will, and normally we would in normal class. Okay, but we can also calculate the energy of that level. Okay, so we're just going to stop for right now.